All right. So we're now in the last part of this textbook. We're talking about biological chemistry, biochemistry. Some topics will come back from organic chemistry. Yeah, these sections are quite a bit of memorizing. I don't believe there might be some math in Unit 12, but today we're going to definitely cover Unit 10. We may touch, get a small introduction to Unit 11, and then on Tuesday we'll finish Unit 11 and then complete Unit 12. Unit 12 is the smallest chapter. I believe that lecture only takes about 45-ish, 50 minutes, right? 45 minutes to an hour to complete Unit 12. So I think as long as we get into an introduction to Unit 11, we should be okay today. All right, so we're talking about Unit 10, and we're going to learn all about carbohydrates, right? Sugars, saccharides. So the first topic we want to cover is we want to take a look at structural isomers, right? We've heard this term before, structural isomers. And we've seen this with, in organic chemistry, we talked about butane, and then we have 2-methylpropane, or commonly known as isobutane, right? But here, right, they both have 4 carbons, 10 hydrogens, but the structure is different, and we consider those to be structural isomers, right? Structural isomers, both of them containing the same molecular formula. So, carbohydrates, sugars, right? There's a lot of isomers when we're dealing with carbohydrates and sugars. Let me get a model kit for today. So the 2 stereoisomers here, right? So we're going to come across a lot of different terms here. So these 2, what we call stereoisomers, right, are non-superimposable mirror images, and we call them enantiomers. All right. So when we have, and I know this is it's a lot of words to say something very simple, is that I can't take 2 different objects that look similar, and I can't stack them on top of each other, right? These are what we call stereoisomers here, and both of them, even though they look the same, right, they're slightly different. This top one here has this pattern here, and we take a look here, and the pattern's different, right? It's in a different location here. This is in a different location here. So even though these are the same, these have been swapped around and they're in different locations. So they may look similar, but they're very different. Right? My right hand and my left hand look very similar, right? If I put this in front of the mirror, some might be able to see a reflection, right? But if I put my hand here and look at the reflection in this window, it looks just like my right hand, right? Is that we can consider these for this topic here, that these are stereoisomers. Right? So like these are stereoisomers. They look the same, right? They're mirror images of each other. If I put this in front of the mirror, this is the reflection we're going to see. But because we can't superimpose, and what we mean by superimposing is I can't take my right hand and superimpose my left hand. And this is what we mean by superimpose. I'm just going to take this, I'm going to put my left hand, put it right on top. I've now superimposed it. And we can see that not everything lines up, right? And when they can't line up like that, when we have stereoisomers, right? These enantiomers that are mirror images, and you cannot superimpose them, right? If we cannot superimpose them, they are considered to be enantiomers, right? We can consider my hands to be enantiomers because I cannot superimpose them, even though they're mirror images of each other. Right? I'll build a small model real quick, a couple of small models. And they may look similar, but we're definitely not going to be able to superimpose them. Let's go with purple. All right. So this carbon is going to be represented by the black atom here. I'm going to put this green one on there. It doesn't matter which one. Like this is, represents hydrogen, but I'm just going to put 4 different colors here. And here, one model. Put that one back here. And a second one. And let me see if these are identical or if we have mirror images. These seem to be. So these are identical molecules, right? These are not enantiomers, right? Enantiomers have to be non-superimposable. My right hand and my left hand are non-superimposable because not everything lines up. If I take this molecule and I superimpose this one, everything lines up. Nothing's out of order. These molecules are identical. These molecules are not, right? Even though they both contain red, green, purple, white, black one in the middle, right? What makes these stereoisomers is this carbon atom here, and it has 4 different things. I'm going to use the word things. I'm not going to use the word atoms, but it's got 4 different things attached to this central atom here, this carbon here, right? Here, right, this has a stereo center right here. So I've got 4 different things attached to it, and we call that chiral. So here's carbon. Let me put some depth into this. Red, green, blue, and white. Right? Just as a reminder, this means that the blue one is kind of going away from you, and then this darkened wedge means that the white one is kind of coming towards you. But this is a chiral carbon. Right, that's our stereo center. That's why these are stereoisomers, because it has a stereo center, and we consider that stereo center here to be chiral because it has 4 different things attached to it. Right, it's 4 different things attached to it. So here, if I did this, let me make 2 of those things the same. This is not chiral. This doesn't have a stereocenter. Why? Because 2 of these things are the same, and the rule for chirality, or the rule for having a chiral carbon, is it needs to have 4 different things. And we can see that it does have 4 things attached to it, but only 3 of them are different, right? We have 2 of these, 1 of these, 1 of these, and we only have 3 different things versus something that has 4 different things. So our enantiomers, 1, they have to be mirror images of each other. if we go back to, well, no, I'll show you the mirror image here, right? If I put this in front of the mirror, this is the reflection that we're going to see, right? So, enantiomer, I have the mirror image, and it has to be non-superimposable, which means if I take this mirror image and I superimpose it, well, the white one and the green one, they line up, but the red and the purple ones don't line up. And some students, well, it's just a matter of twisting it, like you just didn't put it in the right order. So let me match the red and purple ones up. So here, I've now matched the red and purple ones up, and let's see if I can superimpose this. Well, the whites are on opposite directions, so it didn't really line those up, right? So there's nothing I can do here, you know, there's nothing I can do in order to have these there's no way I can just put them in some direction. In order for these to line up and be superimposable, I physically have to move two of these atoms. So now that I've switched them, now these are identical molecules. And identical molecules that have a chiral center, that have a chiral carbon, right? There's no mirror image here. If I put these here like this, well, that's still not a mirror image because the white and the green ones aren't reflected correctly. But if I line up the white one there and I say, okay, I'm going to put the white one there and the green one in the back, and then the red and purple ones don't quite line up. So there's no mirror image here. These are superimposable. They're not mirror images. These are identical. Do they have a chiral carbon? Yes, they have a chiral. How do I know it's a chiral carbon? Because there's 4 different things attached to it, right? If I make a switch, well, now we get our mirror image. There's our mirror image. So it might be an enantiomer. Can I superimpose it? Nope, I can't superimpose it. Non-superimposable mirror images. These stereoisomers are enantiomers. And as we're talking, because this is going to come up in the lab, if I take this green one off of each one of these, I can get a mirror image. Is that here is my mirror image. And I can superimpose them. But what are we missing? Because even though they're mirror images here, these are not enantiomers. And how can I prove that these are not enantiomers? Because there's only 3 groups on here. These are what we consider to be achiral, right? Simply meaning that it's not chiral. So because these aren't chiral, there's no way that we're going to get enantiomers from molecules that are not chiral, right? Thank you for that, Gabrielle. All right, so let's move on here, right? So let's see if we can identify these chiral carbons. And again, I want to emphasize we're not looking for the number of different atoms, is we're looking for the number of different things. And I'll explain that as we kind of go through these examples here, trying to identify different chiral carbons. So if we take a look at that first molecule, is that this carbon here, is this carbon chiral? Zuri? No, why not?
Because it has 2.
Yes, because it has 2 hydrogens here, so it's definitely not chiral. And if we take a look at this, well, I see 4 bonds. Melissa's, is this chiral?
No.
No, why?
Because it doesn't have a 4th.
Because it doesn't have a 4th thing attached to it. There's this thing that's attached to it, there's this thing that's attached to it, and there's this thing. So just 3 different things here. And I'm gonna write this one on the board here, because I want to make sure we're understanding why we don't just look at atoms here. I'm going to write this 2 different ways, and hopefully that'll help this concept sink in. This is going to be CH3, CH2. Actually, you know what? Let me do this even better. How about we do this? Carbon, carbon. I'll put it in expanded structural formula. If we take a look at this carbon here, is this carbon chiral? No, because got hydrogen, 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 and then carbon, right? Same thing with this. This is not chiral because I have 3 hydrogens. This is not chiral because I have 2 hydrogens. And some would think that this is not chiral because we have 2 carbons. But this, in fact, is chiral. Because I really emphasize that we need 3 different things. So let me write this one more way. Here's hydrogen. Here's my chiral carbon. I'm going to put bromine onto it. I'm going to put methyl onto it. And then I'm going to put ethyl onto it. Because that's what this is, right? This is CH3, that this is methyl. And this is CH2CH3, which is ethyl. And this is why I emphasize that we're looking at 4 different things, is that ethyl and methyl and bromine and hydrogen are all different. So this is chiral because this does not look like this. So it's not that I'm looking at carbon, because yeah, this is bonded to carbon, this is bonded to carbon, but I'm looking at this thing over here, and I'm looking at this thing over here, and they're definitely different. So here, this carbon only bonded to 3 different things. It's not chiral, it's achiral. This carbon has 3 hydrogens. This is also achiral. This is bonded to this carboxylic acid functional group, and this carbon is bonded to methyl, and this carbon is bonded to hydroxide, and this carbon is bonded to hydrogen, is that this carbon here is chiral because it's bonded to 4 different things that we have there. So looking at these different types of structures, we can start identifying them. And let me put one of these on the board, and then we can get through that, and then we can go through the rest that are simply on the slide. These lectures, these PowerPoint slides are on Canvas. You are going to see a lot of different figures, different photos, that are not in the textbook. So if you do want to see them, these are on Canvas. There's just a lot of structures, and I really just don't want to draw everything out for biochemistry here. So here, let's go with this. So how we go about identifying this, right? This is only it only has 3 different things it's bonded to. So this is not chiral. I noticed that 2 hydrogens down here. This is not chiral. So now I have to decide between this and see which one is chiral. So this, and I'm going to use a different marker color for this one. When I'm looking at this, here is one thing that I'm looking at. Here's the next thing that I'm looking at. Here is this thing that I'm looking at. And here is this thing that I'm looking at. Is this carbon chiral? Montalyn, is this carbon chiral? Are there 4 different things attached to it? Yeah. This big thing over here, this aldehyde functional group, this hydroxide and this hydrogen here, is that this is a chiral carbon. So now that we've identified that one, it is possible, and it happens quite often, that we have more than one chiral carbon in any of our carbohydrates. If I go to this one here, well, here's one thing that's attached to this carbon. Here's a second thing that's attached to this carbon. Here's this thing that's attached to this carbon. And now there's this thing that's attached to this carbon here. So Bryant, looking at this carbon, is this one chiral? Yeah, because it's got 4 different things attached to it, right? So this is how we need to kind of progress. So both of these happen to be chiral carbons, and it's very possible, again, it happens quite often, where we get 2 chiral carbons. You are going to see this quite a bit where it says CH2OH. It's not that it's one thing attached to it, because here it is right here. It's just kind of written in condensed structural formula, CH2OH. So anything that has CH2OH, you can just, that's not chiral. So there's 2 hydrogens there. And the other thing you can do, anytime we have a carbon that has this carbonyl here, right, here's my carbonyl. If there's a carbonyl there, that's obviously not going to be chiral. So now we kind of have to look at everything else and determine whether it's chiral or not chiral. So here, we know this isn't chiral. Is this chiral? Got this, 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 and then we have all of this, that this is chiral. We'll take a look at the next carbon. There's this hydrogen, there's this hydroxide. I have this attached to it, and I also have this attached to it. And this is different than this, right? So again, another chiral carbon. And we keep going down the line here. We're looking at the 1, 2, 3. This carbon have this, 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 and then we have this down here. And then we take a look at the last carbon. I have this, 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 and then I have all of this. And we can kind of progressively move down and look at all of these chiral carbons. Let's take a look at, how about, right? Just this one. One too many of them here. Yep. All right, CH2OH, right? So here, is this carbon chiral? No, because anytime we see CH2OH, we know that this isn't chiral. Here, if we take a look at this one, we have this thing over here, we have this thing over here, we have this thing over here, and then we have this big thing over here. Is that a chiral carbon? Yeah. All right. This one down here, I have this thing here, I have this thing over here, I have this thing down here, and then I have this big thing up here. Is this one chiral? Yeah, that one is chiral. Let's do this one here. So I have this thing here, I have this thing here, and I have this thing here. Zuri, is this one chiral? No. Do we believe that this is not chiral? right? Because this thing down here looks just like this thing up here, right? These two things are the same. So this would not be a chiral carbon instead. This is chiral, this one's chiral, and these three are considered to be achiral. I'm going to leave this one up here on the board for a second. We want to talk about mirror images and a structural isomer for these. Actually, I'll just redraw on one. That's okay. So here we have this structure here. Chiral carbon here, chiral carbon here, chiral carbon here, chiral carbon here. So we have 4 chiral carbons here. Now, if we want a mirror image of this, the only thing that we need to swap around here are anything that's chiral. Anything that's not chiral doesn't really matter in a mirror image. Okay? So we can still draw this just like this. But its mirror image is that this is now going to be on this side. This one will be over here, and this one will be over here, and this one will also be over here, and then our hydrogens also get swapped. Is that the only thing we need to do is swap around the hydrogen and the hydroxides when we're looking at some mirror image. Right? So if I'm going to do the mirror image of this, I would still put hydrogen here. That really wouldn't matter. But on my mirror image, I'm going to put hydroxide on this side, hydrogen on this side, hydroxide on this side, hydrogen on this side, and we're only concerned with those chiral carbons and swapping those out.
Why don't you put the top of the why don't you switch the
We can. It's not necessary. And let me show you 1, 2, 3, 4, 5, 6. So let me put something together here. And we'll kind of review why we didn't need to do that. I need a double bond. One, 2, 3, 4, 5, and 6. The red ones here are going to represent the hydroxide groups, the OH in particular. CH2. I think I have it all here. Okay. Part of the topic we have not covered just yet. All right. So this structure here, it's already starting to kind of curl up. But here, we can see, I'm going to try and straighten this out just a little bit, but it is curling, which I do need it to curl because that covers a different topic that we have. But here we can see, if I kind of flatten this out, can you see that Montelane? Is that on, oh, come on, I'm trying to keep this together here. Is that we see that these two red ones are the OHs, so that's this OH, it's OH. Then we have this one over here, this is this OH. Oh, I think I have this backwards, but here. What I'm trying to cover is this one here. See how this one just spins around? So it really doesn't matter which direction, if it's pointing this way or if it's pointing this way, because it can spin around, right? It's not chiral, so it really doesn't matter which direction that it's going. This one here, this one's going this way, this one's going this way. It's not coming towards you. It's not going away from you. Is that these are just going in these two different directions, right? So here, again, if I twist it, going this direction, not coming towards you or away from you. But here, if I hold just this two more, these are going towards you, right? In my mirror image that I reflect, if I just do this, that's not really the mirror image, because now they're pointing this direction. For it to be the mirror image, they still have to be pointing in that direction, right? And I can't, if I just twist it like this, well, now they're just pointing in the wrong direction, right? So this is why we can't, that's why we don't worry about this one, and we also don't worry about this last one, simply because I can just spin this around, and because it's not chiral, it's really not affected by this mirror image. So that's the reason that we do not worry. You can, if you had written it that way, there'd be nothing wrong with it. It'd still be correct. We can switch these around, and that would still be correct. If you wanted to put the CH2 OH over here, this direction, it would still be correct, right? But the only thing we're really concerned with is these here. Yeah, does that help explain? All right. So, I think I'm going to leave, I'll just leave one of these up. I don't need both of them up, but I will leave one of those up. So, in organic chemistry, right, we had expanded structural formula, condensed structural formula, line formula. Biochemists are funny people. They want, even though they use the same things, they want to be a little bit different because they're biochemists, right? So something similar to line formula in biochemistry is what we call the Fisher projection. So Emil Fisher came up with this, and we use these bare bone structures to represent carbons, right? Anytime we have an intersection like this, we just understand that there's a carbon there, right? So if I did this here and put it in line formula for organic chemistry, we understand that this is a carbon, this is a carbon, this is a carbon. So here, this is a carbon, this is a carbon, this is a carbon, and if I put All right, so now in this structure here, we understand that, oh, this is a carbon here, and I've actually written it on the actual last one. So this is what we're understanding here. So if we take a look at this structure here, how many carbons are in this Fisher projection? Atom. 6. 1, 2, 3, 4, 5, and 6. Now, along with this here, is that anything any line that's horizontal, these are going to represent atoms that are coming toward you. And any vertical line, right, these represent away from you. And using this model that kept falling apart that I'm not going to try and put back together at this point, is that I was trying to hold it as best together, but here we would represent this with just a horizontal line. We're not going to use the dashes and wedges here, right, because that's for organic chemistry. Here, we just understand that if it's a horizontal line, both of these are coming towards you, right? So horizontal line. If I turn this, horizontal line, horizontal line. And we can see that as it starts to wind up, this is why I was trying so hard not to destroy this, but we can see that it's curling back, right? So this is the molecule here. It's not this, right? Because if I draw this particular molecule, vertical lines represent things going away from you. At no point does it say a vertical line is going towards you. So if I look at this structure, well, the structure doesn't make sense because as I hold it this way, right? If you're looking at this molecule, this atom has to be away from you. And as I turn it, this one has to be away from you. And as I turn it, this one has to be away from you. And as I turn it, oh, this one's towards you. Let me turn that around, and now this one is pointing away from you. This one also has to point away from you, so I need to turn that around. And we get these molecules that look like this. And there's a special reason why we need them to look like this that we'll talk about in just a little bit. But we see that it starts to curl around you, right? So here, we always assume that anything on the vertical line going away from you, anything on a horizontal line, those are atoms that are coming at you. Now, this particular group of sugars that we're looking at right now, they come from a family that we call aldoses. Is that both of these structures are aldoses, right? Why would we call these an aldose? Anna, why would we consider this to be an aldose? What's this functional group? It's an aldehyde. So because these carbohydrates here, because these saccharides here have an aldehyde functional group, this is why we consider them to be aldoses. This represents aldehyde. And this OSE is sugar. Right? Sucrose, glucose, lactose. Right? So this is an aldehyde sugar. An aldose is simply just an aldehyde sugar. We do need to learn how to name these sugars. There's a generic way couple of names you do have to memorize for the exam, but there is a generic way to name all of these particular sugars, right? I'm going to name this sugar, and then I'll have somebody help me name this sugar. Okay. This sugar here is an aldo triose. There's 3 carbons here. So it's not just an aldose, an aldehyde sugar. This is an aldehyde sugar with 3 carbons. So we call it an aldo triose. Kayla Bowden. If this is an aldo triose, then what would we call this one here?
Aldo.
Yes. That this is an aldo hexose. It's an aldehyde sugar with 6 carbons. Aldo triose, aldo pentose, aldo tetrose, aldo hexose, aldo heptose, and we can give these some generic names. I'm going to rewrite this name here. I'm going to make a change, and then Sophia, prepare to help me because I need your help. I'm going to rewrite the name of this one here so we can clearly see it. And 1 carbon, here's 2, here's 3 carbons, this has 4 carbons, 5 carbons, all the way down to 6 carbons. I'm going to make a slight change here. This is not an aldehyde functional group. Right? This is a ketone functional group right here. Right? We have this carbon said this has a ketone functional group. This particular sugar here is what we call ketose. This was aldo hexose. Aldo hexose. Because this was an aldose sugar. It's an aldose sugar, but specifically it's an aldo hexose. You with me, Sophia? All right. So this also has 1, 2, 3, 4, 5, also has 6 carbons. If this is an aldo hexose, what would I call this one here? Ketohexose, right? Genius, yes. That this is a ketohexose. Right? So now we can name these different sugars by determining 1, what functional group that they have. 2, how to specifically call it. So 3 carbons, aldo triose, aldo hexose. Ketone functional group. What would we call this one here? First, Hannah, how many carbons are in this structure here? 4. So what would I call this one with 4 carbons? Keto what? Mono, di, not tri because it's got 4. So mono, di, tri, tetra. So what is it then? Ketotetrose. All right. Gabriella, what would we call this one here? How many carbons are here first? What was that?
5.
Count with me.
1, 2, 4, 5, 6.
So this is a
Ketone.
ketohexose. All right, so we can definitely identify these aldoses, ketoses, and we have a generic way that we call those particular sugars. Now, these sugars give us other isomers. Some of these isomers are what we call D and L isomers. And we do have to be able to identify just kind of, which isomer we have. And how we do that is we take a look at the second to last carbon. Right? We should technically look at the last chiral carbon, but just as a shortcut, just look at the second to last carbon. The second to last carbon, this is the last carbon, this is the second to last carbon. And we look for the hydroxide group. If the hydroxide group is on the left, this is what we call L-glyceraldehyde. If it's on the right, we use D, dextero. Or anybody know how to say right in Spanish? Yes, right, D. All right. So if this hydroxide is on the right, it's D. If the hydroxide is on the left, it's L. But look at the second to last carbon. Don't look at the last one. Look at the second to last carbon. So now we can start looking here. Second to last carbon. And we can decide which one of this is. First, this is the official name. It's ribulose. So this is ribulose sugar here. But is this an aldose or is this a ketose? Ketose, right? Because it has got a ketone functional group. Other than ribulose, what would we name? I'm not looking for D or L just yet, but what would we name ribulose as just as a generic name? Samantha. A generic name. This is 1, 2, 3, 4, 5 carbons. It's a ketose sugar. So Samantha, what would we call this sugar? We are going to use penta, yes, or pent, right? But we still need the prefix because it's a ketone sugar. It's a ketose. We're going to say keto pentose. So this is ketopentose. Is ribulose the D or L isomer? What is it? D. Because here's the last sugar, here's the last carbon, here's the second to last carbon right here, that the hydroxide group is on the right, that this is D. So for sorbose, Hosue, is this the D or L isomer for sorbose? What is it? D. So we're looking at the second to last carbon, and we look at the hydroxide, and is it on the right or left side?
Right side.
So this, as you're looking at it, is this hydroxide on the right side or on the left side?
Oh,
Left side, right? So this is going to be the L isomer. All right, we get a little switched around. We're good. We're good. Milex, idose, D or L isomer? D isomer because this is on the right-hand side. Is this the D or L isomer? This is the, which isomer? Which carbon are we supposed to look at? Is this the second to last carbon? Which one is the last carbon?
Oh, no.
Where's the second to last carbon?
It's in the middle. Yeah.
So this is a
D.
D isomer because we always do. So again, don't ever look at not the last carbon. We always look at the second to last carbon, right? Second to last carbon, and we can identify which one that is there. So getting to this other topic here. So this over here, right? This is what we call a Fisher projection, right? These are the bare bone structures, right? Looks like a fish scale, but here we have glucose, and this is the Fisher projection for glucose. This is what we call a Hallward structure. This is also glucose. You have to memorize what this structure looks like. You have to know the Fisher projection, and you have to know the Hallward structure for glucose. As far as glucose is concerned, is this the D or the L isomer of glucose?
D.
D. Second to last carbon, the hydroxide is on the right side. This is the D isomer of glucose. As far as the Fisher projection goes, you have to memorize a couple things about glucose. One, glucose is an aldose sugar. And everybody here should know what an aldehyde functional group looks like. Glucose has 6 carbons. One, 2, 3, 4, 5, 6. And the last one is always just CH2OH. So we memorize this structure here. If you can memorize this structure, how to draw it, the next step to make it glucose isn't too difficult. Right? What makes this glucose are the locations of these hydroxides, and in particular the hydroxide on 2, 3, and 4. The hydroxide on carbon 5 tells us whether it's D or L. But carbons 2, 3, and 4, this is what tells us whether it's glucose or not glucose. So if I put the hydroxide here and this hydroxide here, and I'll put this hydroxide here and I'll put this one over here, we can say, is this glucose? Okay, it's not glucose. Well, how come it's not glucose? How do you know? Because this should be over here, and right, these hydroxides should be in a different spot. So as far as glucose goes, one, let's memorize this structure here. This was my way of memorizing it. I sat in the exact same spot you do. Me and Adam were talking about this yesterday. I sat in the same spot that Adam is sitting in right now. I came here. Professor Kennedy was my professor when I started. But when I was trying to memorize this, I just kind of came up with this, and this is how I memorized it. I'm not flipping you guys off, right? But I did use my middle finger, right? So I'm going to point it this direction, so I'm not flipping you guys off. I don't want anyone to run to the dean saying, Alex flipped us off in class, I can't, right? But if I do this and just kind of flip myself off, my fingernails, the way my fingers are pointed, are telling me where the hydroxide goes. Is that here, this is pointing this direction, hydroxide goes here, hydroxide goes here, hydroxide goes here, hydroxide goes here, and I've now drawn the D form of glucose. And Professor Kennedy's going like, Alex, what are you doing? Right? I'm sitting there taking my example, right? But this is just, you don't have to memorize it like that, but this is how I memorize it, right? And then it gets funny because like it happens all the time. I have like 6 or 7 students doing like this, which one, trying to find glucose. It gets kind of funny. But anyways, this is, if I put this over here, well, now I just have the L form of glucose, right? It's still glucose, because this hydroxide, this hydroxide, this hydroxide matters, and this one is just simply telling me D or L. But that is our Fisher projection. As far as the Howard structure goes, we're going to see something similar here. Is that carbon number 2, carbon number 2, carbon number 3, and carbon number 4 is what dictated that this was glucose. As far as the Howard structure goes, the Howard structure goes, we'll learn how it goes from this to this, because it will. This can transform into this, and this can transform into this, vice versa. And we'll learn that in just a minute here. Howard structures identify what we call alpha and beta isomers. For the Fisher projection, the second to last carbon, the hydroxide, indicated whether it was D and L. For the Fisher projection, we're going to take a look at what we call the anomer. I'm not going to say carbon number 1. In this case, it happens to be carbon number 1. But we're going to identify the anomer. This is our anomer. This is our anomeric carbon. It's the carbon to the right of the oxygen. This carbon here, that is our anomer, and it's the carbon that's to the right of the oxygen. So here's my oxygen, and if I go to the right, this is my anomer. This is my anomeric carbon. Now, on the anomer, we're looking for the hydroxide group. On this structure of glucose, this Howard structure, here's my anomer, and the hydroxide is pointing down. Is that this is alpha. If the hydroxide is pointing up, it's beta, right? But we're always looking at the anomer that's there. Here's my anomer. We locate the hydroxide group. If it's pointing up, it's the beta isomer. If it's pointing down, it is the alpha isomer. So we can identify D and L, alpha, beta, in these structures. Now, as far as glucose is concerned, carbons 2, carbon 3, carbon 4. And again, in a Howard structure, that's also what we're looking at here. Here's carbon number 1, carbon number 2, carbon number 3, and carbon number 4. This is carbon number 5, and this is carbon number 6. But again, this is 3. We're going to look at 2, 3, and 4. 2, 3, and 4. Right, left, right. And here, down, up, down. And that's our pattern, because I'm looking at the hydroxide. Hydroxide's pointing down, hydroxide's pointing up, hydroxide's pointing down. I want to make sure that there's 6 carbons here. I keep writing, this should be 5. I have 6 carbons. It's a hexagon shape. It goes down, up, down. I know that this is the alpha version of glucose. Right. So how this occurs, right? When I built this model here, we noticed that it curled. When these form ring structures, notice that carbon number 6 is not part of that ring structure. Is that what happens here is, here's carbon number 5, here's carbon number 1, and this, we can see that this oxygen here, and here's the model of it, here's the double bonded, here's my carbonyl, it's my carbon number 1, and here's the oxygen on carbon number 1. And without even any work, if I just hold it like this, we can see it's touching carbon number 5. Here's carbon number 6, and here's carbon number 5. So carbon number 5 right here and that oxygen are touching, is that this is how that ring closes. Is because it's so close together, it ends up connecting there and making that bond. Okay? And so we get this closed structure here. And how we get alpha and beta, well, that depends. Because if this carbon number 1 is pointed this direction, it's going to bond one way. Let me hold it up this direction here. There we go. If I hold it this direction here versus holding it some other direction here. So here, if we twist this around, right? Once this connects, depending on the way this is turned, if that carbonyl is pointing up, that's how we get that hydroxide in that beta form. When it closes, if it's pointing in the downward direction, we get the hydroxide on the bottom, so we get two different forms there. Again, we're going to notice that this is glucose. How do I know it's glucose? Because it has 6 carbons, 1, 2, 3, 4, 5, 6. And my patterns on 2, 3, and 4 is down, up, down. This is glucose. This is beta glucose. So here, is this glucose? No. Because carbons 2, 3, and 4, this is up, up, down. Is this glucose? Down, up, up. Is that glucose? No. Down, up, down. This is glucose. But as far as alpha beta goes, is this alpha or is this beta?
Alpha.
Alpha, because the hydroxide's pointing down. This is my anomer, oxygen. Carbon to the right is my anomer. Hydroxide pointing down is alpha. Is this the alpha beta version of this particular sugar?
It would be alpha.
Alpha, because it's pointing down. Is this alpha or beta?
Beta.
Beta, because it's pointing up. Right? So I was looking for the hydroxide group on that particular structure here. Oh, real quick. Is this D or L? Nobody knows. How do we determine D and L isomers?
If it's on the archive is on the left. and
We
if it's not on
need
the left, it's
we need this structure. If you don't have that structure, I don't know if this is D or L. I don't have the Fisher projection. I don't know if this is D or L. All I know is that this is alpha. I know this is alpha. I know this is beta. I don't know if any of these are D or L because we don't have that Fisher projection. Just like looking at this, is this the D? I'm sorry, is this the alpha or beta? I have no idea. I need the Howard structure in order to determine whether it's alpha or beta. So Howard structures determine alpha, beta. Fisher projections determine D or L. If you want to know both of them, you need both of them. If you're only given one, we can only determine one of those isomers there. Ketone structures, not an aldehyde. This is a ketone. This is the second sugar that you need to know for the exam. right? You need to memorize the structure of fructose. Fisher projection, Haworth structure, and you have to be able to identify alpha, beta, DL isomers. This is D-fructose. So fructose is a ketose sugar. It's not an aldose, it's a ketose, and there's my ketone functional group. Second to last carbon, hydroxide on the right. This is definitely our D isomer. Now, as far as the anomer goes, this is the reason why I didn't say that the anomer is carbon number 1. Where do we locate the anomer? Well, the anomer is the carbon to the right of the oxygen. So here's my oxygen, and I'm going to go to the carbon to the right of that oxygen, and that happens to be carbon number 2, and this is our anomer. This is the anomeric carbon. And on the anomeric carbon, this is what decides alpha and beta. What we look for, and I'm going slow because I want everybody to catch this, this is what I'm looking for. I'm looking for hydroxide on the anomer. Here is the anomer, and we're looking for the hydroxide that's on the anomer. Zuri. In this structure, where's the hydroxide pointing? On the anomer. Down. I know that there's hydroxide here, but this hydroxide's on carbon number 1. And I want the hydroxide that's on the anomer. And this happens to be the hydroxide that's on the anomer. Pointing down, alpha. Here, my anomer. Pointing up, this is beta. Okay. So this is how we tell. So when we have these ketose sugars, this is how we tell alpha and beta. So we're not looking where this large group is here. We're just looking, find the anomer, and then whether that hydroxide group is pointing up or whether it's pointing down. Now, all of these sugars here, all these carbohydrates here, what they have is they have a lot of oxygen. When we have all these oxygens, right, what we have is we have an abundance we have all these electrons here. And these, even though this is a ketone, because we talked about oxidation, if we look at an oxidation reaction, this is a little bit from organic chemistry. When we oxidize aldehydes, we oxidize primary alcohols, we get an aldehyde. So here's a simple aldehyde. And if we oxidize this aldehyde, we get carboxylic acid. When we oxidize a ketone, we get no reaction because ketones don't oxidize. Ketones don't oxidize. Ketose sugars like fructose, these oxidize. And the way that these oxidize is that these ketose sugars, they undergo something they call isomerization. It comes from the word isomer, right? Is that there's a rearrangement because there's so many electrons there. It's so electron rich is that it can actually convert into an aldose sugar. Go from fructose and convert into glucose. Once we get the aldehyde, then it can be oxidized. So even though that this is a ketone, it's a ketose sugar, is that these can still undergo oxidation. We're going to have that experiment today. We're working with Benedict's reagent today. It's this really beautiful blue color, and we're going to oxidize, try and oxidize different sugars. Right? So know that ketose sugars can oxidize. Okay? So all these carbohydrates, right, are what we call saccharides. Monosaccharides, disaccharides, oligosaccharides, and polysaccharides. If it's just one, so here, this is a monosaccharide. Right? This is a monosaccharide. Let me draw the Howard structure for this. So if I take this monosaccharide here, this is one sugar, and notice that I'm not putting in all the additional hydrogens, right? It's kind of like line formula. We don't really have to write in all of the hydrogens, right? I know that there's a hydrogen here, but my concern is I need to know where the hydroxide goes. This tells me that it's alpha, down, up, down. This tells me that it's glucose. This is, in fact, alpha glucose, right? Because I have this structure here, that this is going to be beta, right? Beta glucose, or sorry, this, yes, alpha, this is L-alpha glucose. There we go, all right. But anyways, when we have these single units, this is a single unit. When we have these single units, this is what we call a monosaccharide, right? Monosaccharide. If I take this monosaccharide, because it's just one, and I bond it to another monosaccharide. So here, these are two monosaccharides. Monosaccharide, monosaccharide. But if I bond them together, now they're bonded, this is what we consider a disaccharide. Right? So mono, they're just singles, two of them together, disaccharide. Horrible shape. There we go. Now I've added a third one. This is not a trisaccharide. Okay? Mono, di, anything between 3 and 10 saccharide units, right, is what we call an oligosaccharide. Anything larger than 10, polysaccharide. So we're not going to do tetrasaccharide, pentasaccharide. No, it's either, if there's 5, it's oligosaccharide. If there's 9, it's oligosaccharide. If there's 10, it's oligosaccharide. If it's 11 or more, polysaccharide. So mono, di, oligosaccharide, and then we have our polysaccharide chains. All right. So there we go, monosaccharide. Here's glucose. This is alpha glucose. It's also in the D isomer there, so this is alpha D glucose. Here we have fructose here. So disaccharide, oligosaccharide, and this is just kind of a zoomed in picture of what we see here. So this is a polysaccharide here. All of those there happen to be glucose units, and just different examples of all of these saccharides here. Now, any carbohydrate or sugar that can be reduced is what we call a reducing sugar. If it can be reduced, it's a reducing sugar. All monosaccharides, whether it's an aldose, whether it's a ketose, if it's a monosaccharide, we can oxidize it. Right? It can be reduced. Now, we use the term reducing sugar. I'm going to try and briefly explain reducing sugars. Again, I mentioned, right, in biochemistry, there's just terms that have to be a little bit different, but they come from general chemistry, organic chemistry. Let's take a look at copper plus zinc sulfate. If we go back to, these are like rules of oxidation. Copper goes from 0 to copper to plus. Zinc goes from +2 to zinc 0. Let's backtrack. So here, zinc is reduced, copper is oxidized. If zinc was reduced, copper is what reduced it. So we'll backtrack from what I said earlier, make that correction. So copper is what reduced it. Copper is the reducing agent, right? Copper is the reducing agent. So here, I have this in red, and it's bolded. I wonder why I would do such a thing, right? All monosaccharides and all common disaccharides, except for sucrose, are reducing sugars. Right? They're all reducing sugars. And we're going to see that in our reaction today for the experiment. Right? So reducing sugars, even if it happens to be this, remember this is an aldehyde structure, C, carbonyl here, hydrogen off the end. We have an aldehyde, undergoes oxidation, and we can get that carboxylic acid. So even a ketose sugar can do this, right? Because our ketose sugars can isomerize into an aldehyde, then those will oxidize. So again, all monosaccharide, doesn't matter what monosaccharide. We can go back up here to the beginning and look at all of these. These are monosaccharides, these can be oxidized, right? These can be oxidized, right? These can be oxidized. All monosaccharides and all common saccharides can be reduced, except sucrose. So, polysaccharides, can this be oxidized? Is this, no, right? Because it's not a disaccharide, a common disaccharide, it's not a monosaccharide, so we can't reduce that. So let's take a look at some common. We'll get to sucrose, but we first need to understand these common disaccharides. So you don't have to necessarily memorize this whole reaction. There's some important information here you do need to know, but you don't have to specifically memorize this reaction here. This is a reaction in order to make a disaccharide. Right, we get one glucose and another glucose, and they bond together through this oxygen here, and we get a disaccharide. So this happens to be a disaccharide, and this oxygen here, we also call it an oxygen bridge, right? Has a special name that this is a glycosidic bond. This oxygen here is a glycosidic bond. Now, we go through this reaction through dehydration, right? Dehydration is how we get this reaction because here we see our water, right? Water is H2O, so we remove this hydroxide here, we remove this hydrogen here, that gets our water, undergoes dehydration, and we form this oxygen bridge here that we call a glycosidic bond. Now this glycosidic bond here, actually, I'm going to put this upward. This has a specific name. Right? Is that this is a glycosidic bond. Now, before this bonded, is carbon number 4 or carbon number 1 the anomer here? Carbon number 4, is that the anomer, or is carbon number 1, which is to the right of the oxygen, the anomer? Carbon number 1, this is our anomer. And it's always our anomer that determines whether it's alpha and beta. Hydroxide pointing down that this is alpha. So after it makes that bond, because we use the anomer to make this bond, this is an alpha, carbon number 4, carbon number 1, it's an alpha 1, 4 glycosidic bond. Because this bond occurred from the anomer that was alpha, and the oxygen is bonded between carbon number 1 and carbon number 4. Because we can have different bonds here. I'm not going to bond it just yet. If I'm going to put these into a dehydration reaction and bond these together, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, this carbon and this carbon, and I'm going to bond those together now. So before I bonded it, I'm using this anomer, and this sugar is in the alpha or beta position. Beta. Because it's pointing upward, this is beta. And when I bond it together, this particular glycosidic bond is a beta, and what carbons is it bonded to? 1, 4 glycosidic bond. This is a beta 1,4 glycosidic bond. let's do one more. Actually, we'll probably end up doing two more. Anomeric carbon, but this anomer is the one that's going to make the bond with its oxygen here. So we're going to
So the alpha 1650.
this is what was that?
There'll be alpha.
Alpha
16.
1,6
Glycosidic
glycosidic bond. Because it was in the alpha position, that was the anomer, it was the alpha bond between carbon number 1, carbon number 6, alpha 1,6 glycosidic bond. Make one more here. And we're gonna stick with Montelane here to help me out with this one. And Montelane, I want you to pay special attention to the anomers. Pay close attention to the anomers. Because we always use the anomers to determine alpha and beta, right? Oh. All right, so Monty, can you see this? You can see this okay? All right, so here, where is the monomer in glucose? What number carbon is it?
It's 1.
Carbon number 1. So this is our anomer, right? And is this anomer alpha or beta?
It's alpha.
Alpha, right? So this monomer here is alpha because it went down. Now, is this, where's the anomer in fructose?
2.
2, this one right here. And is this alpha or beta?
It would be beta.
Beta, perfect. And like this one, we said we look at the carbons that are involved in there, and we alpha because this is in the alpha position, and we always use the anomer that's involved in the glycosidic bond. So what happens here? What do you think we could name this?
Well, it would be
We named the isomer first. So is this alpha or is this beta? Let's look at, ignore this bottom one. Is this alpha or beta?
it's beta.
It's what?
No, it's alpha.
Okay, so we know it's alpha.
Right.
Now ignore the top one. Is it alpha or beta?
It's beta.
Beta. Alpha, beta.
Mhm.
And what carbons is it between?
1, 2,
1, 2
glyceric,
glycosidic bond. Right? Because this anomer was not involved, right? So we're not going to say alpha-alpha because this anomer wasn't involved in that glycosidic bond. But since both of these anomers are involved in that glycosidic bond, we use both alpha and beta to describe that glycosidic bond. But the difference between this saccharide here, if we take a look way back here when we talked about these things being isomers, right, is that, wrong slide, where is it at? Where is the reducing sugars? There we go. Reducing sugars. In order to reduce, we need an aldehyde. In order to reduce, we need an aldehyde. This disaccharide here, oh, there it is. When this opens up, this can open up. This carbon can open up. We get an aldehyde. And that aldehyde can oxidize. We can oxidize that. So here, this can open up. It can turn into this aldehyde structure, and we can oxidize it. This, we can't. This is not going to turn into an aldehyde because it's connected to this one here. It's connected to this. It's not going to oxidize. It's going to remain as it is, but this portion here can be oxidized. Well, it's the same thing. If carbon number 1 and carbon number 6 can't break apart and free up to turn into an aldehyde, well, that means this can't either. This is sucrose. Sucrose is not a reducing sugar. Can't be oxidized, right? And it can't be oxidized because both of these anomers are involved in that glycosidic bond versus only one of those anomers being in that glycosidic bond. So because there's a free one here that's not involved in that bond, we can oxidize this, right? This can turn into an aldehyde, this can oxidize, can't turn into an aldehyde, can't oxidize. But it is the only common one we're going to worry about as far as not being able to be a reducing sugar. Now, as far as these disaccharides go, I mentioned you don't have to memorize this reaction, but you do need to know that glucose and glucose make maltose. You do need to know that glucose and fructose make sucrose. And you do need to know that galactose, this is where we get the term lactose, this is galactose, and glucose make lactose. Right? Galactose, down, up, versus glucose, down, down, right? And we get that beta 1,4 glycosidic bond there with glucose, with lactose. All right, and we're going to take a small break in just a bit. We're almost done with 10, and then we'll touch on 11 for a little bit, and then we'll be good for the lab. So just these last topics here. Well, this is a polymer. Polymers are really large molecules, all made up of the same monosaccharide, right? The same repeating unit that we call monomers, monosaccharides, monomers. So these polysaccharides, right, starch, glycogen, cellulose, they're all polymers that are made of repeating glycose units, right? There's one glycose bonded to another, bonded to another, bonded to another, right? And those make up different structures of starch, glycogen, and cellulose. So starch, primary storage polysaccharide in plants, right? Potatoes, full of starch, right? Those the storage unit in plants. Then we have, these are what we consider to be just amylose, right? Chains of amylose. And all of these happen to be, this is glucose, glucose, glucose. These are all bonded together using alpha 1,4 glycosidic bonds, right? And there's no branching here, right? These even though it's like 4,000 units here of different glucose, there's no branching that occurs here, right? And these are actually considered pretty small, okay, even though it's those 4,000 units. But again, all repeating glycose units, all 1,4 alpha, right, glycosidic bonds. And then we have some larger ones here. So once they start to get a little bit larger, we notice some branching occurs, right? Again, these are all glucose units, all bonded alpha 1,4, except the branch. The branch is bonded at alpha 1,6. The branch is bonded at alpha 1,6. All right. And then we have glycogen, right? Glycogen, this is how we store glucose, right? Plants store glucose, not with glycogen, right? This is how we store glucose. And this is what we consider to be highly branched, right? Is that we see a lot of branching, not just one or two that splinters off. But here, highly branched units, all bonded alpha 1,4 except for the branch point. The branch point's bonded alpha 1,6. And then we get cellulose. Right? Cellulose isn't used for glucose storage. Right? Cellulose is used for structure. Right? We think of blade of grass, we have those cellular walls there, right, made of cellulose, makes it pretty rigid, and we can use those for structure. Now, there's particular enzymes that we have that will break apart these glucose units. Right? So we take in carbohydrates or these sugars, we can break most of it down. Some of it gets stored as glycogen. We break some of that down, but we do have the enzymes that will break apart those glucose units. We don't have the enzyme to break apart beta 1,4 chains, right? We can break apart these alpha 1,4 chains, but we don't have the right enzyme to break down these here, right? These are beta 1,4. But you know, we can think of this is why we don't process fiber, right? We don't process fiber because of these here, but it will make this kind of stepwise structure here versus one that's strictly horizontal. Right? Fiber, right? My grandbabies love corn, but you know what happens if you don't chew your corn, right? My kids will inhale corn, comes out the same way it goes in, right? I've changed plenty of diapers, and they swallow their corn, and the inside of the kernel, you know, will be empty. We can break that down, but that outer shell, that cell wall, this cellulose of that kernel, not happening, right? Not happening. So that's fiber, and we just don't process fiber. And that will complete Unit 10. So we're going to take a break for about 15, 20 minutes. So let's come back at 10:15. We'll come back at 10:15, and then we'll start with Unit 11.